Tree languages are a superset of linear languages. While in linear languages, the ground terms of a language form a linear sequence, in tree languages, not surprisingly, the terms form something that's more tree-like. Consider a language with an object constant a and two unary function constants, f and g. Some of the terms in the language are shown here. At the top of the tree, we have our object constant a. To the left, f of a. To the right, g of a. Applying f to f of a, we get f of a. Applying g to f of a, we get g of f of a, and so forth. As with linear languages, we can write an inductive rule of inference for tree languages. The tree induction rule of inference for the language just described is shown here. Suppose we know that a schema phi holds of a. Suppose we know that whenever the schema holds of any element, it holds the term formed by applying f to that element. And suppose we know that whenever the schema holds of any element, it holds of the term formed by applying g to that element. Then since we've covered all of the possible terms in the language, we can conclude that the schema holds of every element. In order to see an example of tree induction in action, consider the ancestry tree for a particular animal, say a dog. We use the object constant rex to refer to the dog. We use the unary function constant f to refer to the father of the dog, and we use g to refer to the mother of the dog. Finally, let's say we have a single unary relation constant p. That's true of a dog if and only if it's purebred. Now we write down the fundamental rule of dog breeding. We say that a dog is purebred if and only if both its father and its mother are purebred. All right, this is a bit oversimplified on several grounds. Properly, the father and the mother should be of exactly the same breed. Also, this formalization suggests that every dog has an ancestry tree that stretches back without end. However, let's ignore these imperfections for the purposes of our example. Suppose now that we discover that our dog Rex is purebred. This gives us an additional axiom, and given this information, we know that every dog in Rex's ancestry tree must be purebred as well. We can prove this with a simple application of tree induction. Here's a proof of our conclusion. We start with the premise that Rex is purebred. We also have our constraint on purebred animals. First, we use universal elimination to instantiate the second premise, and then we use biconditional elimination on the biconditional in line 3 to produce the implication on line 4. On line 5, we'll start a subproof with the assumption that X is purebred. Now we can use implication elimination on our assumption and the implication on line 4 to produce the conclusion on line 6. And we can use AND elimination to pick out the first conjunct. We then use implication introduction to discharge our assumption, generate an appropriate implication, and use universal introduction to universalize the result. So much for the F case. What about the G case? We still have to prove that it's true for the G case. Well, we can repeat the process almost exactly with just G in place of F and produce a similar result, here shown on line 14. Finally, we can use the tree induction rule on the sentences in line 1, the base case, line 9, the inductive case for F, and line 14, the inductive case for G, and thereby derive our desired overall conclusion.